The topic of this lecture is to show you how to do calculus on parametric equations. We did a little bit of that already in the last lecture, okay, but I'm going to show you again how to do the derivative, and then I'm going to show you how to do a bunch of other stuff as well. Okay, so here's what we're going to do. Let's review really quick what we mean when we say parametric equations. Okay, instead of, here, let's write this down. Instead of having y equals a function of x, let's say capital F of x, instead of that, we have x is a function of a third variable t. Let's say x equals f of t, and y is also a function of t. We'll say y equals g of t. Okay, and you can see all about this in the previous lecture. All right, so what I want to do is re-show you again how to find the derivative of x with respect to y. Okay, so let's write finding dy dt. dy dx. Okay, so since y is not a function of x, then you can't just take the derivative of y with respect to x. Okay, but what we can do is we can write dy dx equals dy dt divided by dx dt. Okay? In other words, g prime of t divided by f prime of t. Okay? Now I personally like this way of writing it better. I think there are reasons why that's better, because I think it makes it easier to remember. You can memorize this, but if you were to forget it, I'm not sure how you would bring it back to your mind. I think you'd have to go through looking it all up again. But this formula, if I ever forget it, I can always remind myself of what the formula is, because it's just like fractions, right? Isn't it like if I were to write 3/5? Isn't that the same thing as 3/2 over 5/2? So if I know that I'm trying to calculate dy dx, I can remember, oh yeah, you just put them both over dt, because then the dt's cancel. Okay, now you might ask the question, oh, are we supposed to cancel the dt's? Okay, the answer to that is no, you don't actually cancel them. Okay, you don't do this and cancel them, because what you want to do is you want to calculate this thing and also calculate this one. Okay, let me give you an example. Let's do an example here. We're not going to do an example of everything today, because we will do it in the next lecture. One big example where we practice everything, but for right now, let's do this. Let's suppose we had x equals 5t squared plus 1 and y equals 3t plus 2. Okay, so let's find the derivative of y with respect to x. Well, here's what I'm going to do. First, I'm going to calculate the derivative of both with respect to t. I'm going to write, okay, let's find dx dt. That would be 10t. Let's find dy dt. That would be 3. So then dy dx, I just remember that that equals dy dt divided by dx dt. So that would be 3 over 10t. And there's the derivative of y with respect to x. And you could use that to find the local minimums and maximums on the graph, or to figure out when the graph is increasing or decreasing. Okay? All right, now, what if you want to calculate concave up and concave down? Then you need the second derivative, right? Let me show you how to find the second derivative of y with respect to x. So finding the second derivative of y with respect to x. Okay, so the key there is to remember that the second derivative of y with respect to x is the derivative. Sorry that the screen keeps moving. I can't seem to stop that from happening. The second derivative of y with respect to x is the derivative with respect to x of dy dx. Whoops. Right? The second derivative is the derivative of the first derivative, correct? So, what do? We do a very similar trick as before. We put each of those over dt, and we get the derivative of dy dx, which we calculated up above, with respect to t, divided by the derivative of x with respect to t. That's how you find the second derivative. Let's put a little bit of space in there so things aren't so jumbled. Okay? Now I'll show you another example here of why I think this Leibniz notation with the d's is much easier than the prime notation in this case. Because if you wanted to write that in the prime notation, what would it be? Here's dy dx, g prime of t over f prime of t. And then you would have to do the derivative of that with respect to t, so the prime of that, divided by the derivative of x with respect to t, which is f prime of t. Now let's look at the top. Wouldn't you have to use the quotient rule there? So you would get g double prime times the bottom, which is f prime, minus the top, which is g prime, times the derivative of the bottom, darn it, which would be f double prime, divided by the bottom squared, And then that whole thing, sorry, let me fix that too. It didn't come out very well. That whole thing gets divided by f prime of t. You see, this is something that I think is a lot harder to remember. We have g double prime times f prime minus g prime times f double prime over f prime cubed. That certainly works. And you're welcome to memorize that definition. But myself, personally, I like this one better. Okay? I'll try to organize this nicely in a table at the end. Okay, so let's practice that previous example. Finding the second derivative. I don't remember the functions exactly that we did in that first example, but I remember basically. So let's say we have x equals, I believe it was 5t squared plus 2 or something like that. Might have been plus 1 or something. Let's not worry about that. And y equals 3t. Let's do plus 1 this time here, okay? All right, so let's find the first and second derivatives. So the first thing I do is I find dx dt. So that's 10t. Then I find dy dt. That's 3. So the first derivative, sorry, made a mistake there. Let me fix that. There we go. Derivative of x with respect to y is dy dt over dx dt. And what's that equal? It equals 3 over 10t. Okay? Now, let's find the second derivative. Of y with respect to x. So what's the formula for that? It's the derivative of the first derivative with respect to x. We take the derivative of that with respect to t. So in other words, the derivative of this with respect to t. Okay? And then we divide that by the derivative of x with respect to t, which I already calculated above. Okay? So what is the derivative of 3 over 10t? What's the derivative with respect to t? Well, remember, that's the same thing as 3/10 times t to the negative 1. So the derivative will be negative 3/10 times t to the negative 2, right? So in other words, it'll be negative 3 over 10 t squared. Calculating simple derivatives should not be at all difficult for you by the time we've gotten to Calc 3, okay? On the bottom, I put dx dt. What was that? That was 10t. And now I simplify. What am I going to get? I'm going to get negative 3 over 100 t cubed. There's the answer. Okay? So that's how you do the first two derivatives. If you wanted to find the third derivative, you could do it the same way. It's the derivative of that answer with respect to t divided by dx dt. Okay? All right. Now for the rest of these, I'm going to take the formulas for things like arc length, area under a curve, surface area, things like that you learned in Calculus 1 and 2. And I'm going to show you how to just use some algebra to convert those into formulas for the same thing with parametric equations. Okay, so let's do this. Finding the area under a curve. You know what that means. That means the area between the graph and the x-axis, right? Okay, so remember that to find that area, you integrate y with respect to x, correct? Remember, if you had something like, let's write this down, if you had y equals capital F of x, then the area under the curve would have just been the integral of capital F with respect to x, right? Remember that? Okay, so whatever y equals, you integrate that with respect to x in order to find the area under the curve. So in this case here, let's look again at what we have up here. We have y equals g of t. So I can replace that y there with a g of t. Okay, but there's a little bit of a problem here. If I put dx on the end, that's now not going to make any sense. How do I take a function of t and integrate it with respect to x? That's not going to match up. It's not going to work. If the variable in my integrand is a t, then I'm going to want to be integrating with respect to t. In other words, I want the integral to end with a dt, not a dx. But I certainly can't just cross that out and write dt instead. I can't do that because the differential of x is not the same as the differential with t. I have to find a way to convert from dx into dt. And there's an easy way to do that. We just multiply times dt and then turn around and divide by dt. You see, once again, it is just as if those dt's would cancel. So dx dt times dt is the same thing as dx. But I don't cross those out. I leave them there. That's the formula. Okay, so you can write it two ways. You can write the integral of y times dx dt times dt. Now we don't usually write that last times. We usually write integrals just like that. So that's one way to write it. The integral of y times dx dt, you integrate that with respect to t. Okay, or if you prefer, you could write it as the integral of g times f prime, because that's dx dt is f prime. That's how you find the area under the curve. Okay. How about arc length? Do you remember the formula for arc length? Normally, when you just have x's and y's, no t's, the formula for arc length was the integral of the square root of 1 plus the derivative of y with respect to x squared. Remember that? So all we have to do here is change this to an integral with respect to t. Okay? Well, that's going to be pretty easy to do. I'm going to work down instead of across because it does take more steps, but none of the steps are hard. Okay? So that equals, first of all, let's do this. Let's write down what we already know. What is dy dx? Okay, we went over that up above. Dy dx is dy dt divided by dx dt. Okay? And let's also fix that dx at the end. It needs to be a dt, right? How did we fix that in the last integral? We rewrote dx as dx dt times dt. Okay, now we're just going to do a little bit of simplifying, that's all. I want to factor something out of the square root. Okay, so in order to do that, okay, let's do this. We're going to have 1 plus dy dt squared divided by dx dt squared, correct? And then I have this dx dt and then a dt. Now, I said a second ago that I'd like to factor this out, but to be honest with you, I just realized it'll be easier, instead of factoring that out, it'll be easier to distribute this. So here's what we're going to do. I'm going to take that dx dt, and I'm going to just move it around to the front of the square root. I'm not doing any math here, I'm just moving it. I mean, technically that is math, but what I mean is I'm not changing any of the players that are on the stage. I'm just rearranging them. Okay, now let's distribute this dx into the square root. When you do that, it's like passing through a portal. Let's write that red arrow like this. When the dx passes into the square root, is it still going to be a dx? No, it's going to be dx, sorry, not just dx, dx dt. When it passes into the square root, is it still going to be dx dt? No, it'll be dx dt squared, right? So we'll have dx dt squared times the 1 plus dy dt squared over dx dt squared. And then at the end of all that, outside the square root, we got a dt. Okay, and now we distribute this into here. And do you see what we're going to end up with? Integrate the square root of, so on that red arrow right there, we're going to have dx dt squared, right? And then we got a plus, and then we got this arrow. What's going to happen? That will cancel with that, won't it? What do we have left? dy dt squared. There we go. That's our answer. Don't forget the dt at the end. That's the formula for, what is this that we're calculating here? Arc length, right? That's the formula for arc length of a parametric curve. If you want to write that in the prime notation, that would be the integral of the square root of f prime of t squared plus g prime of t squared. That's the formula for arc length for parametric curves. Okay, and then one more thing you learned in Calculus 1 and 2 was how to find the surface area of a surface of revolution. Let me remind you what that meant. So let me just write here. I'm just going to write surface area, okay? Finding surface area. But do you remember that, let's review again. What is a surface of revolution? Okay, let's put some axes here. Okay, now remember that if you had a function that looked something like this. You could, that would be where y is a function of x, okay? You could rotate that around the x-axis. Remember doing this? And you end up with something that would look like this, except it would be three-dimensional. Remember that? That's called a surface of revolution. And what did we learn how to calculate? You should have learned by now how to find the volume of that and the surface area. Okay, now to find the surface area of that, I don't know if you remember learning that or not, but the nice thing about surface area, we always teach after arc length, because calculating the surface area starts with writing down the arc length function and then just putting an extra little bit onto it. If you remember, this is from Calculus 2, okay? For arc length, I'm going back here to Calculus 2 where you had y as a function of x. So I'm not doing parametric right now, okay? Let's just go back to rectangular where y is a function of x. Remember, arc length looked like this.
You did too. It's a nice superpower ability.
Remember that? And then to find surface area, all you had to do was take that same formula as arc length and then just insert in front of the square root. We just inserted a 2 pi f of x. Or you could write 2 pi y. Let's do that. Let's write 2 pi y. Some people prefer to put the 2 pi in front. I always do myself. Okay, but for these purposes, I'll leave it inside. Okay, so now exactly the same idea. For parametric calculus, you want to find the surface area of that thing. You just write down the arc length formula and you just insert a 2 pi y in front of the square root. Okay, so let me erase that green stuff. Let's write down the arc length formula. We just did it.
I'm just tired.
And in front of the square root, we just enter a 2
No, I didn't.
pi y. And there's your surface area formula. If you want to write that in prime notation, it would look like this. 2 pi y square root f prime of t squared
Yeah. I hope we just do some more.
g prime of t squared with a plus in between.
More annotating.
Okay, that's the surface area formula. That's for when you're rotated around the x-axis. If you rotate it around the y-axis,
Yeah, yeah.
then let me just draw that. Suppose you have something more like this,
So I might as well take my dues.
and you want to rotate around the y-axis. And you want to find the surface area. The only thing that would change, look at the formula over there.
Yeah,
What do you think is the only thing that would change? That would become a dy dt squared, and this would become a dx dt squared, but we're just adding those together, so it doesn't matter what order they're in.
Yeah, me too.
So we don't have to change those at all, right? Only thing is that this would change to an x. That's all. There's the only difference. Okay, and last one.
Yeah.
Let's find the volume of these things.
I'm not.
So again,
That's the only thing I'm not buying.
if you rotate around the x-axis, how do you find the volume of that? Remember in Calc 1, I think it was, might have been 2, but I think it was Calc 1. You found the area using the disk method. That's the only one we're going to worry about. Let's just use the disk method. There's also washers and shells and all that, but let's just do disk. Okay? So remember the volume for that was very easy. It was just integrating pi y squared, remember, with respect to x. So the absolute only difference here is that we want to convert that dx to a dt. So we integrate pi y squared times dx dt with respect to t. In prime notation, I would write it like this. Pi g of t squared f prime of t dt. And if you want to rotate about the x-axis and find the volume, then that would be integral of y x squared dy. So that would be pi. I think I said y a second ago instead of pi. Integral of pi x squared dy dt dt. In prime notation, that would be the integral of pi f of t squared g prime of t dt. Okay, so that's pretty much everything that you learn in Calculus 1 and 2 of what to do with derivatives and integrals converted into their proper form if you had parametric equations. Let me summarize this in a nice chart. Okay, so here is a summary of everything we learned in this lecture. Okay, we have parametric equations, x equals f of t, y equals g of t. If you want to find the first derivative of y with respect to x, dy dx, then in Leibniz notation, that would be dy dt divided by dx dt. Or if you prefer in prime notation, that would be g prime divided by f prime. Now if you want the second derivative of y with respect to x, that would be equal to, in Leibniz notation, that is the derivative of the previous derivative with respect to t divided by dx dt. Or in prime notation, g double prime times f prime minus g prime times f double prime divided by f prime cubed. Okay, now the area under a curve. In Leibniz notation, that's the integral of y times dx dt. You integrate with respect to t. Or in prime notation, it's the integral of g times f prime with respect to t. Moving down, we have arc length. In Leibniz notation, that's the integral of the square root of dx dt squared plus dy dt squared, integrate with respect to t. And in prime notation, it's the integral of the square root of f prime squared plus g prime squared. For a surface area of a solid of revolution, if it's rotated about the x-axis, okay, in Leibniz notation we have the integral of 2 pi y times the square root of dx dt squared plus dy dt squared. In prime notation, you integrate 2 pi g times the square root of f prime plus g prime. And for rotating about the y-axis, the only difference is changing the y to an x if you're in Leibniz notation, and the g of t to an f of t in prime notation. And then finally, the last thing we learned was calculating the volume of a solid of revolution. If it's rotated around the x-axis, that's just the integral of pi times y squared times dx dt, or pi g squared f prime. And if it's rotated around the y-axis, we have the integral of pi x squared dy dt, or pi f squared g prime. So that's a lot of information. I don't expect you to memorize these formulas, although if you did, That would make it easier for you, not having to look stuff up. You should definitely, though, endeavor to not have to look that first one up. At least that should be something that you should be able to remember. Okay, now tomorrow, or I shouldn't say tomorrow, but in the next lecture, lecture 3, we will look at one graph of some parametric equations, and we will practice calculating these things and figuring out the maxima and minima and the area under the curve and things like that. Okay, have a good day.